So this is just another concept bite video, this time on O2 quenching. So the kind of key to quenching by molecular oxygen is molecular oxygen's molecular structure. It's molecular orbital arrangement. And we can see I've just taken the 2p orbitals here and combined them. I end up with a sigma star set and a pi star set, and I fill them with the 8 electrons that I have, and I see that the ground state of molecular oxygen is a triplet with a pair of unpaired electrons in that antibonding pi orbital. So that unpaired because of Hund's rule. They don't want to pair up. It's a lower energy configuration if they're unpaired, but more to the point, it's also a lower energy configuration if the spins are aligned in the two separate orbitals. If I take just that HOMO orbital, that pi star orbital, and I can arrange the electrons in it in 3 different ways. In my lowest energy, that is that Hund's rule set, that a pair of spin-aligned electrons in 2 separate orbitals. If we use symmetry labels, that set is called the 3 sigma G minus set. Higher in energy, I have 2 possible orbitals. I have the set where I have the spins unaligned, so the spins anti-parallel in 2 separate orbitals. That set's 1 sigma G plus, and that's the highest energy set. And slightly lower in energy, I have the set where the spins are anti-parallel, so paired, but they're together in a single orbital. So electrons want to be paired if their spins are anti-parallel, and want to be in separate orbitals if their spins are parallel. And that middle set is the 1 delta G set. If for whatever reason I generate that 1 sigma G plus set, that highest energy set, it will rapidly decay to that 1 delta G set. So it will stay as a singlet form, but it will rapidly decay to that 1 delta G. And that 1 delta G set has quite a long lifetime associated with it. In water, somewhere in a region around 4 microseconds. In D2O, it's even longer, 62 microseconds. I can't form singlet oxygen directly by excitation of the electron from that 3 sigma G minus set to either of the other sets, because it's strictly forbidden by spin, symmetry, parity, selection rules. It doesn't occur. And so if I want to generate singlet oxygen for whatever reason, it's going to be generated involving another molecule. And that other molecule kind of involvement is really, really important. It gives us very interesting properties of the singlet oxygen, but it also is quenching the other molecule which is involved. So, the quenching that occurs with molecular oxygen is of a Dexter type form. And here I have just a very, very quick recap of what Dexter energy transfer is. It's exchange of electrons. So I'm moving an electron between a donor and an acceptor, and then between an acceptor and a donor. Overall transferring energy from my donor to my acceptor molecule. But I do that by this kind of concerted exchange of electrons between my donor and my acceptor molecules. Because I'm physically moving electrons, it only occurs over very short distances, less than 20 angstroms. And in the case of O2 quenching, it's almost certainly collisional in its kind of foundation. Not just when things get close, but kind of really based on traditional collisions that we think about in chemistry reactions. So what happens in the actual case where I have molecular oxygen involved? Well, here I've got this triplet excited state. This is this molecule in green, and I've got my O2 molecule here in blue. And what happens is, because that O2 orbital isn't filled, the excited state electron on my donor is going to want to transfer into one of the HOMO orbitals of the O2. And if I've got a Dexter energy transfer, at the same time, one of my electrons on O2 will transfer to the donor, which leaves me with a arrangement which has transferred the energy from the donor to my O2. And we can see, if we look at the alignment of the electrons, I've gone from a triplet state donor and a triplet state ground state molecular oxygen to a singlet ground state of what would have been my donor molecule and a singlet O2. And in this case, I've got this 1 sigma G, but I've already said this 1 sigma G rapidly decays to this long-lived 1 delta G. Once I've generated O2, which is very, very common in the presence of triplets, that O2 can then go on to react because of it being this long-lived excited state. But the key things to remember are the mechanism is a Dexter energy transfer mechanism, so it's physical exchange of electrons between my donor and my O2 molecule. That it happens mainly with excited state triplets. It can happen with excited state singlets, but the yield of it is incredibly small. So we're mainly thinking excited state triplets. And so I end up generating the ground singlet state of my donor molecule and this excited state singlet of my O2. Hope this helps. I'll be back with more.